Hello, welcome to section 3 of chapter 1. In today's video, we're going to be discussing the numbers of nucleons as well as how to use and critically think about some numbers we're going to learn about today that are from the periodic table, as well as all the information that we learn across this chapter. Now, we're going to begin by talking about two very important numbers that we're going to encounter multiple times in the exam. Now, the atomic number is something that you should be familiar with from honors chemistry. Now, there is a separate or an alternate name for the atomic number that is used a lot in England and in the Cambridge curriculum, which is the proton number. So know that the atomic number and the proton number are synonyms of each other. They're referring to the exact same thing, which is the atomic number on the periodic table for a specific element. The atomic number or proton number is usually symbolized with the letter Z. So if you see Z somewhere on a problem, it is more than likely standing in for the atomic number of that element or the proton number. Now, the proton number, atomic number, is the number of protons in the nucleus of the atom. So it's very straightforward and very, like the name implies. The number is specific to each element, like we mentioned before. That means that that number defines and identifies that element, meaning that elements are not going to have a different proton number anywhere else. So, for example, if I bring in the periodic table, and this is the periodic table that you will find in all AS exams. So I will highly recommend, we have this in the core document on Schoology, I will highly recommend that you become familiar with this document and that you learn how to read it. Now, like it says on the key, let me make this a little bigger. Like it says here on the key, the atomic number goes right above the symbol for the element on this particular periodic table. So, for example, oxygen has the atomic number 8. Let me actually use my highlighter here. Oxygen has the atomic number 8. Fluorine has atomic number 9. We have astatine has atomic number 33. And let's do one more. Silver has the atomic number 47. So the atomic number is found right on top of the element, and it is the number of protons that that element has, regardless of what isotope or what ion of this element that is. It's always going to have the same number of protons. So if he has 47 protons, that's silver, no doubt, no questions about it. If he has 8 protons, it's oxygen. If he has 9 protons, it's fluorine, not oxygen anymore. All right. So the proton number, which is found right above that symbol, the symbol is going to be what identifies that element. Now, the Nucleon number is what we call the mass number last year in honors chemistry. And again, Nucleon number is simply just an alternate name that is used in different countries and in the Cambridge curriculum. The Nucleon number, or mass number, is often symbolized by the letter A. And the mass number, what it shows is the number of protons plus the number of neutrons found in the nucleus. So that's why it's called the Nucleon number, because it is the total number of nucleons, or protons plus neutrons, because those are the nucleons. You will not find the mass number or proton or nucleon number on the periodic table. And this is something that you need to understand. The Nucleon number or mass number is not on the periodic table. So let me write that here, so make the point. Not on periodic table. What you find on the periodic table, the number that we're used to seeing on the periodic table, and I'm going to bring this back just for a second here. This number below the elements is not the Nucleon number. That number below the elements is the relative atomic mass, which we will discuss later on. But this is a very, very, very common misconception that students have. On the periodic table, we can find the relative atomic mass, which is a different number than the nucleon or mass number. The nucleon or mass number will be given to you usually in one of two formats, which I will mention in the next slide. Now, the number of protons, if you ever want to know the number of protons of an element, all you have to do is look at the proton number, atomic number. So that's something that you should keep in mind. If you're ever asked how many protons does this particular element have, all you have to do is look at the atomic number or proton number on the periodic table, and that is the number of protons. Instead, if you want to know the number of neutrons an element has, that is a little more detailed. It requires a little more critical thinking. We have the Nucleon number, which is the number of protons plus the number of neutrons. And we have the atomic number, which is the number of protons. So if we grab our Nucleon number or mass number, and we subtract the proton number or atomic number from it, what we will be left with is the number of neutrons. So in order to figure out the number of neutrons an element has, you will need the Nucleon or mass number. And that's why they're given to you with isotopes, which is our next point of conversation. Isotopes, which we have mentioned before, are atoms of the same element which are not identical. Now, this was one of the big points that Dalton got wrong in his theory. Dalton said that all elements of this or atoms of the same element are identical, but that is actually not the case. Later on, we discovered the neutrons, and therefore we discovered isotopes. Isotopes are atoms of the same element with different nucleon numbers. So they're atoms of the same element because they have the same number of protons. But they have different nucleon numbers, therefore meaning, because the protons can change, they have this different number of neutrons. Isotopes of an element have pretty much the same chemical properties, but they have slightly different physical properties. Specifically, their mass and their density is different. Since neutrons actually have a fairly hefty mass when it comes to subatomic particles, they actually are going to either increase or decrease the mass of an element when you add or take away neutrons. And because the volume of that element stays the same, the density of that isotope is also different, because we're changing the mass but not the volume. And if we remember from middle school, the density of any compound, or density of anything really, is equal to its mass divided by its volume. Well, if we change the mass, let me use a different color. If we change the mass of the atom by having a different isotope, but not the volume, then the density has to change. And so the density and the mass of isotopes are different because they have different number of neutrons, which weigh different amounts. And so the isotopes weigh different amounts. So there is two main formats for writing isotopes, and you have to be given this information because the format in which we write the isotopes are where we find the nucleon number or mass number. For example, carbon has three different isotopes. There's what we call carbon-12, carbon-13, and carbon-14. You might have heard about this if you ever heard about carbon dating, which you probably have in school. Carbon dating uses carbon-14 and carbon-12, and the differences in the two in things that are organic in order to age different things, whether fossils or whatnot. So carbon can be written as carbon-12, carbon-13, carbon-14. A few things to point out here. We have carbon-12, carbon-13, and carbon-14. These are three different isotopes of carbon. There is no carbon and then isotopes of it. When we talk about isotopes, we are talking about different versions of the same element, but there is no main version. There is no one isotope that's the isotope and then isotopes of that element. We can think of this like with twins or triplets. When you're referring to siblings who may happen to be triplets, there is no main triplet and then triplets of that one person. We have three individuals who are triplets of each other. Same thing with isotopes. We have carbon-12, carbon-13, and carbon-14. There is no main isotope. Carbon-12, carbon-13, and carbon-14 are all different versions of carbon and therefore isotopes of each other. Now, Is there a more abundant one? Yes, carbon-12 is the most common, the most abundant type of carbon, but that does not make it the main type of carbon. It just makes it one of the three isotopes, which happens to be the most abundant. Now, what do these numbers mean? The carbon-12, 13, and 14, those numbers, 12, 13, and 14, are the nucleon number of that element. They are of that isotope. So when we say carbon-12, we're referring to the carbon isotope with a nucleon number, mass number 12. When we say carbon-13, we are referring to the isotope of carbon that has 13 as its mass number. When we say carbon-14, same thing, carbon isotope with a mass number of 14. This is one way to write, one for notation of writing the isotopes. The other one is like this, and this one's used more in chemical reactions. We use the symbol for the element, C, and then we put the mass number or nucleon number on the top left and the proton number on the bottom left. And you can see here, 6, 6, 6. All three of the carbons have 6 as its proton number because that's how many protons are in carbon. If we change that number, it will no longer be carbon. It will be something else and therefore not an isotope here. So carbon, we have the 6 in the bottom left every time because that's a mass, the atomic number. And then on the top left, we have the mass number, 12, 13, 14. If you ever forget which one's which, always remember the mass number is always bigger than the proton number because you always have at least one neutron. The only time that this is not the case is with hydrogen 1, which is the only isotope that does not have any neutrons. But other than that, the mass number will always be bigger than the atomic number, and the mass number always goes on top. The bigger number on top, the smaller number on the bottom. So if we look at this and we start using our brain, which we'll do a little further in the next, in a few slides, we can start to decide how many protons, neutrons, and electrons these elements have, or at least how many protons and neutrons. We'll talk about electrons in a second. So carbon has 6 as its proton number. That means that all 6 or all 3 of these isotopes of carbon have 6 protons. Now, where they differ is the number of neutrons. That's what makes them isotopes. Remember, in order to get the number of neutrons of an isotope, we need to grab the nucleon number and subtract from it the proton number. So if we're looking at carbon-12, that means the nucleon number is 12 minus the proton number, which is always going to be 6 for carbon. That means that there are 6 neutrons in carbon-12. Carbon-13, on the other hand, has 13 as its nucleon number, minus 6, which is its proton number. That means we have 7 neutrons in carbon-13. And then carbon-14 has 14 as its nucleon number and 6 as its proton number. And so 14 minus 6 means that we have 8 neutrons in that carbon. So this is something that we can easily, or should be able to easily use critical thinking to figure out. Next, we're going to look at ions. And now ions are something that we studied in fair detail in last year in honors chemistry. Now, you should be able to figure out the number of ions, but something that we did not really talk about was the relationship between ions and isotopes. And the reality is that it doesn't matter what the isotope is, you can have ions of the different isotopes. So, for example, if we're talking about electron gain, and if you remember from last year, a gain of electrons makes an anion or a negative ion. Whenever we gain electrons, we are going to have a negative ion being formed. Now, if we have chlorine, and that chlorine gains 1 electron, then we're going to go from Cl, the atom, the neutral atom, gaining 1 electron, becoming chlorine -1. That we learned in honors chemistry. But we have to realize that it doesn't matter which isotope of chlorine this is. In this particular case, this is chlorine 37. meaning chlorine has a nuclear number of 37, atomic number of 17. When it gains that one electron, these two numbers don't change because, again, the atomic number is the number of protons, and the nucleon number is the number of protons plus neutrons. Neither of these two numbers are affected by the electrons. So when chlorine gains that one electron, in this case chlorine 37, all that is happening is that the charge of the chlorine, which we put on the top right of the symbol, changes to -1. It gains that -1 from the electron. And the 37 and the 17 stay the same. So what does that mean here? That means that we can have, in this particular case, we go from Cl37, which has 17 protons, 17 electrons if it's neutral, because if we remember, anything that is neutral has the same number of protons and electrons. So when it's a neutral atom, same number of protons and electrons. So it has 17 protons because of the atomic number, 17 electrons, and that should be a 2, not a 1. And it has 20 neutrons. Has 20 neutrons in it. And that has 20 neutrons because 17 or 37, which is the atomic number or the mass number, minus 17 gives us those 20 neutrons. When we have the electron has no protons, no neutrons. It only has electrons. So if we look at this across, there's 17 protons in this original neutral chlorine. There are no protons in an electron. So when we form this ion, the number of protons stays at 17. The same happens with neutrons. We had 20 neutrons originally in this atom. We add one electron, which has no neutrons. So the number of neutrons stays at 20. The electrons are what changes. When we go from this neutral chlorine, which has 17 electrons, and then we add one electron to it, forming an anion, a negative ion, we now have one more electron in Cl-, which is 18. If this happened with chlorine 35, it will be the exact same thing, only we will have, instead of 20 neutrons, we would have 18 neutrons. That's the only difference if we have a different isotope. So we can form ions of all the different isotopes of the elements. Now, if we have the opposite, cation formation. So electron loss means that we will have a cation. And if you remember from honors chemistry, cations means that we have positive ions. So we lose electrons, we create a positive ion, a cation. So this happens with metals usually, something like magnesium. So we have magnesium 25. Magnesium has a 25 is the mass number, 12 is its atomic number because it's 12 protons. So magnesium 25 in its neutral form has 12 protons and therefore 12 electrons because it is neutral, and 13 neutrons. Again, how do we get those 13 neutrons? We have 25 as the nuclear number, minus 12, which is the proton number. That gives us the number of neutrons, which is 13. When magnesium loses electrons, we can show those electrons as being a product in a chemical reaction because they're being lost. Magnesium, again, the nucleon number and the proton number don't change. They remain exactly the same, 25 and 12, because these are not affected by electrons. What does change is the charge of that ion. The magnesium charge now goes to +2 because it has lost 2 electrons. We can think about it this way. Protons, there are 12 protons in neutral magnesium 25. When they lose electrons, it doesn't affect the protons because the electrons don't have protons, so we say 12. Neutrons, same thing. We have 13 neutrons in magnesium 25 neutral. When it loses the electrons, doesn't matter. It doesn't affect the neutrons because there are no neutrons in those electrons. However, we have 12 electrons in the original neutral magnesium. When that magnesium loses 2 electrons, we now only have 10 electrons because 12 minus the 2 lost is 10 electrons. Again, this could have been magnesium 23, could have been magnesium 26. It doesn't matter because the protons and neutrons are not affected by the charge. Only the number of electrons are. So we can have different ions form with the different types of isotopes. And that is something very important to keep in mind because, again, in AICE Chemistry, you're going to be asked to use a lot more critical thinking. And so you're going to have to use a lot more of this brain capacity to say, okay, I can ignore the protons and the neutrons because they're not affected by the gain or loss of electrons. And so they're going to remain the same from the neutral isotope to the ion isotope or charge isotope. So just to kind of summarize everything we've seen, if I wanted to know the number of protons of an element, all I need to do is look at the proton number, which can be found on the periodic table. If I wanted to know the number of electrons, well, if the atom is neutral, if it has no charge, then the number of protons is the number of electrons because they cancel each other out. But if I have an ion like the ones we just saw, the number of electrons are going to be the number of protons minus the superscript or the charge. So I'm going to put here not just superscript, but you can also call this the charge. It's a number on the top right of the ion. So if we do the proton number minus the charge or superscript, including the sign, whether it's positive or negative, then we'll get the number of electrons. And finally, the number of neutrons is going to be the mass number minus the atomic number. Or backwards, I guess also, the mass number is the number of neutrons plus the atomic number. All right. So you also should be able to move this around a little and be able to figure out things like the mass number and whatnot by using some simple mathematics. So now that we know this, let's put this into the test. So the last thing we're going to do here is look at an actual AICE Cambridge question. And this is a question that actually comes up a lot, almost in every paper too. The composition of atoms and ions can be determined from the knowledge of atomic number, nucleon number, and charge. Complete the table. So here what we have is two lines on a table, which give us the atomic number, nucleon number, number of electrons, number of protons, number of neutrons, and the symbol for different isotopes, atoms, whatever you want to call them, including the charges. Now, notice that this question is worth 2 points or 2 marks. That means that probably each line in this question cost 1 point. So this requires critical thinking. You have the knowledge. I mean, this last slide that we looked at is in itself the way to answer this question. We use this knowledge that's summarized in this slide to answer this question, but you are required to really think critically and carefully about what you're doing because you're not given all the information. You're only giving some of the information. So when we look at this, we have the atomic number for an element, the number of electrons, and the symbol. We have Li63+. Now, when we're looking at this symbol is probably what's going to give us the most information, if we think about it, that we can then fill everything else out with. Because the symbol, if you remember, has the symbol for the element, the charge, which we actually could have found out because it's 3 atomic number and 2 number of electrons. So we can do that math for the +1 charge. We'll get to it in a second. We have the top left number is 6 and the bottom right is 3. If you remember, the top left is the nucleon number and the bottom left is the atomic number. Well, we have the atomic number already, so you can see a 3 there. So the nucleon number here is 6, which we get from that symbol. Even if you didn't remember which was the nucleon number, which was the atomic number, as long as you remember that the left numbers are nucleon and atomic, then you know that you have the atomic number here if you use critical thinking. It's 3, so then 6 has to be the nucleon number. Now, for the number of protons and number of neutrons, if we remember, number of protons are going to be equal to the atomic number. Number of neutrons are the mass or nucleon number minus the atomic number. Actually, let me write nucleon just so there's no confusion here. So nucleon minus atomic. And the number of electrons is going to be the atomic number minus the charge. Now, we already have that here, so we don't need to worry about it, but I wanted to include it just in case. So the number of protons is the atomic number. So the atomic number here is 3, so this is also 3. Now, the number of neutrons, on the other hand, is the nucleon minus the atomic number. The nucleon number we have is 6. The atomic number is 3. And so the number of neutrons is 6 minus 3 is 3. That gives us the first line. So that gives us 1 point. I would recommend that whenever you see these symbols, that you do double check that you have the charge on there, the nucleon number and the atomic number, because sometimes they will give you partial symbols and they have stuff missing that you have to fill in, but not in this case. Now, if we go down to the next part, then we see that we have a bit in the second line of the reverse, right? Instead of them giving us the numbers and then having blanks for the number of protons, number of neutrons, they gave us the number of protons, neutrons, and electrons, and then asked us for everything else. Well, if we keep this in mind, then this is actually pretty straightforward. It's kind of like Sudoku. You just look at the blanks and see where you can get them from. The atomic number we know is the number of protons. So if we know that the number of protons for this element is 26, then we know the atomic number is 26. Now, for the nucleon number, that requires a little more math, because we have that the nucleon number minus the atomic number here equals the number of neutrons. Well, if we rearrange this, because what we're looking for now is the nucleon number, then if we rearrange this, the number of neutrons minus the atomic number, which is the number of protons, will give us the nucleon number. And that's just a simple amount of critical thinking or math. So if we do the number of neutrons, which is 32, minus the atomic number, which is 26, 32 minus 26. So again, number of neutrons, plus, not minus. Sometimes I get tired. So when we rearrange this, we put the minus atomic on the right side. That's why plus the atomic number. So number of neutrons plus the atomic number. So 32, which is the number of neutrons, plus 26, which is the number of protons, gives us 58. And so 50, let me make that a little bigger, gives us 58, which is our nucleon number. Now, for the symbol, this is where we have to put all this information together, right? So the first thing that you need to do in order to figure out the symbol is, okay, what element is this? Because in order to do a symbol, we need the symbol of the element from the periodic table. We can figure that out from the atomic number. The atomic number here is 26. So all we have to do is pull up our periodic table, which you will have to do on the AICE exam fairly often. We pull up our periodic table and we look for the element with the 26 atomic number. The element with the 26 atomic number is iron, and so our symbol is Fe. So we're going to use Fe as our atomic number, as our symbol. So we're going to go over here. Fe is going to be our symbol. And then we got to remember, on the left side for symbols, we have the nucleon number on the top, the atomic number on the bottom. Well, we already have those numbers. Our atomic number is 26, as we just saw. Our nucleon number is 58. Finally, now you might think you're done, but you have to be careful because we need to figure out whether or not this element or this atom has a charge. In this case, we have 26 protons and 23 electrons. Well, again, if we have 26 protons and we have 23 electrons are negative. If we subtract the number of protons or the atomic number, the number of protons or the atomic number from the number of electrons, which is the, it comes from the question itself, we'll get 26 minus 3, which is a plus 3 charge. And do use your logic. Do not rely just on memorization. Think about this. We have 3 more protons, which are positively charged, than we do electrons, which are negatively charged. If we have more positive charge, the ion should be positive. And because it's 3 more, it should be positive 3. And so that will give you the charge. If we look at our mark scheme or basically our answer sheet, this is the answer sheet for the problem, and it shows us that we did indeed get all the right numbers and that we got both points. And again, this is 2-mark question. That means each line is 1 mark, meaning that in that first line, 633, how we read in 632, we will get no point for that line. And then the second line, 2658, and then the symbol. Have we forgotten the +3? Have we used the wrong symbol? Even if we had put a lowercase f instead of a capital F, which is wrong, that is not the appropriate symbol for iron, we would not have gotten the point in that line. So you gotta be very careful with how you are writing on these questions for the Cambridge exams. That is it. That is everything we have for chapter 1. I will see you in the video for chapter 2.